These are the practice problems for lesson 5, and this is problem number 1. You're supposed to take this quadrilateral, which is A, B, C, D, and dilate it with the center of dilation at point 0, 0, and dilate it with a scale factor that's determined by B prime here. They don't tell you what the scale factor is. You have to figure that out. So remember that the distance from the center of dilation to each of these vertices is the unit length for that vertex. So this length right here is the unit length for point B. And this point B prime, you just have to look at it and think about it and figure it out. This is 1 unit, and it looks like from here to B prime, it's 2 of those lengths. So this scale factor is going to be a scale factor of 2. So the scale factor of the whole dilation will be 2. Now you can check that by using the coordinates. So scale factor of 2. So B is 3 units along the x-axis. B prime is 2 times that 3, or 6 units along the x-axis. And then B is 1 unit along the y-axis, and it's 2 times that 1 or 2 units along the y-axis. So the coordinates of B are 3, 1. The coordinates of B prime are 6, 2. So you can multiply each coordinate, and it's because one reason you can do that is, or the reason you can do that is because this dilation starts at 0, 0. You can't just simply multiply coordinates if the dilation does not start at 0, 0. So in this case, this is 3 units out, so 2 times that 3 units is going to be 6. And this is 1 unit up, so 2 times that 1 unit is going to be 2, and those are the coordinates that you end up at. You can use that same idea for each of the other 3 points. Now, the other 3 points, you can look at it and just tell. If this is a scale factor of 2, it's this rectangle right here. That's 1 unit, the diagonal. And so 2 units times 2 is just going to be another one of those rectangles, the diagonal of that rectangle. So it's going to take you to that point. Same with this point. This is a rectangle that gets you out 1 unit, and then 2 units is twice as far. And this is just 1 square here, the diagonal of that square. 2 times that length is going to get you out to here. You can also use the coordinates and multiply by 2 to figure this out. So let's look at A. The x value for A is negative 2. So the x value for A prime, or the dilated image of A, is going to be 2 times negative 2, which is negative 4. So this is nice practice of multiplying a positive value times a negative value. 2 times this negative 2 gets you out to negative 4. And the y coordinate was positive 3. So 2 times 3 gets you up to 6. So right there. D prime, or the image of D, is 2 times negative 3. Gets you out to negative 6. So it goes out to here. And 2 times negative 2. So this is a negative 2 right here. So this point is negative 3, negative 2. So 2 times that negative 2 gets you to negative 4. So this point is negative 6, negative 4. So again, multiplying a positive number times a negative number. And the last one is the image of C. So C prime. This is a positive 1, negative 1 are the coordinates. So 2 times 1 is 2. And 2 times a negative 1 is negative 2. Then you connect each of those points. You get A prime, B prime, C prime, D prime. Take away all the other scaling lines. And you get, this is a scaled image of A, B, C, D using a scale factor of 2. Now, one more time, notice that each of the lengths, because it's a scale factor of 2, each of the lengths are twice as long in the dilated image, and they are always parallel. So AB is parallel to A prime, B prime. They're all going out and creating parallel lengths. This length is parallel to this length, so BC is parallel to B prime, C prime. CD is parallel to C prime, D prime. And A prime, D prime is parallel to AD. But the angles, what about the angles? The angles are always congruent. So all of these angles are equal. They're the same size. So this angle right here is the same size as this angle that goes, that is at C prime. All right, this is problem number 1. This is problem number 2. And there's some triangles that get dilated. And the first question is, what is the center of dilation? When you find the center of dilation, you look at each of the vertices. You draw lines that connect each of the corresponding vertices. And those lines are going to intersect at the center of dilation. It's one of the reasons that each of the sides in dilations are always parallel to each other, because these lines are all related in their position and they all intersect at the center of dilation. So the first question is, what is the scale factor that takes image A to image B? So what scale factor? So this is the center of dilation. So what scale factor takes image A to image B? Now these are just estimations. So you take this distance here. This is the unit distance then you're working with. This is 1 unit. Then how many times that unit does it take to get to B? So I estimated, I just went out to here and estimated a point here. So this is 1 of those units. So this is 1, this is 2 times. If I take another one of those units, it's going to get me out to about here. And from that, you can see that it's about 4 times. It might not be exact, and they're not asking you to be exact. They're just asking you to estimate the scale factor. So the scale factor, an estimated scale factor, would be 4 times. So to take image A to image B with the center of dilation at D. Now they ask, if you reverse it, if you take B to A, what's the scale factor? Well, always, if you have a scale factor going in one direction, if you reverse that direction and dilate the image in the opposite direction, it's always going to be the reciprocal of the scale factor. So scale factor equals 4, it's 4 times. To go back, image B to go back to image A, this length is 1/4 the total length. So 1/4 is the reciprocal. So it's a scale factor of 1/4 to go from B back to A. So this length right here is 1/4 this total length, and that is called the reciprocal. So 4 and 1/4 are reciprocals. Okay, the last part of this is, what's the scale factor that takes C back to B towards the center of dilation? And that tells you that the scale factor is going to be a fraction. And the question is, what fraction of DC, this entire length, is dB? So what fraction is this length in dB of the whole length, which is DC? So again, you just have to estimate. And so this is the last piece here. So if I can find out how many of these pieces are in this whole length, then this is going to be a fraction of that. It doesn't quite make sense, but a little bit hard to follow. So I took this piece and I just went back in this direction an equal amount. And from that I could see, well, it's probably about an equal amount to get to here. That means I'm dividing up the entire length, DC, into 3 equal parts, and 2 of those parts are dB. So 2 of those parts are 2/3. So the scale factor to take image C back to image B is going to be 2/3. All right, so to summarize the whole thing, to take A to B, that was a scale factor of 4. To take B back to A, that's a scale factor of 1/4, and that is the reciprocal. So if you reverse the dilation, you're going to use the reciprocal. And to take C to B, that is a scale factor of 2/3. So dB is 2/3 of the length to DC. All right, problem number 2. This is practice problem number 3. You're given a triangle A, B, C, and you're asked to scale this triangle to triangle A prime, B prime, C prime with a center of dilation at 0, 0 and a scale factor of 2. Well, because the center of dilation is at 0, 0, you can actually multiply the coordinates by the scale factor, which is 2. But I'm going to show you both ways. I'm going to count first. So if I count, and I have to go out, scale factor of 2, so I count 1 time. So this is 1, 2, 1, 2, and then I just repeat that. So that's 2 times, 1, 2, 1, 2. So the point for C prime is going to be right here. The point for B prime, count 1, 2, 1, 2, and do that count again, 1, 2, 1, 2. So the point for B prime is going to be right here. And for A prime is going to be right here. This is 1, 2, 3, 4, 1, 2, and then count that again, 1, 2, 3, 4, 1, 2. And you start to see different ways to do this. Here's a diagonal of this square that's 2 by 2. So this is the second diagonal to go to here. Same thing down here. It's the same size square down here. This is 1 diagonal. This is 2 diagonals. And this is a rectangle. It's 4 by 2 rectangle, but this is the diagonal to go from here to here. And then it's just the same diagonal again, because it's a scale factor of 2 to get from here to A prime. And finally, notice that you can multiply the coordinates. So 2 times a negative 2 is negative 4. And 2 times a negative 1 is negative 2 is negative 4 again. So this is negative 4, negative 4. Let's look at this one over here. 2 times 8, 2 times 4 is 8. And 2 times 2, negative 2 is a negative 4. So this is 8, negative 4. And 2 times 2 is 4. And 2 times a negative 2 is negative 4. So several different ways to find these points, A prime, B prime, C, and C prime. So this is A prime, this is B prime, and this is C prime. Now the problem asks you to take triangle ABC and use a scale factor of 1/2. So now we're going to shrink it by 1/2 each of these lengths. So we're going to draw lengths from the center of dilation to the vertex and cut that length in half and get a scaled or a dilated triangle A double prime, B double prime, and C double prime that has a scale factor of 1/2. All right, so I connect each vertex with the center of dilation, and then you just take 1/2 that length. And you can also, again, use the coordinates. 1/2 of a negative 2 is a negative 1. 1/2 of negative 2 is a negative 1. So it gets you to that point right there. 1/2 of 2 is 1. 1/2 of negative 2 is negative 1. So it gets you to that point right there. And 1/2 of 4 is 2. And 1/2 of a negative 2 is negative 1. So it gets you to that point right there. So a couple of different ways to do it. It gets you this blue triangle, which is A double prime, B double prime, and C double prime. Then the last question is the blue triangle, the double primes, is that a dilation of the green triangle? So A prime, B prime, C prime. And the answer to that is yes. If you drew lines, let's see if I did that. Yeah, I did. If you drew lines from the center of dilation to each of the corresponding vertices, it's a straight line that goes through each of those points. So that tells you that it's a dilation. And also a dilation of a dilation is going to be a dilation of the beginning figure. So they're all related. But notice, if the primes, if the green triangle is a dilation by a scale factor of 2, then to get back to the black triangle, the original one, that's this dilation of 1/2. So to take this point to here, that's 1/2. And if you remember, the double primes, the blue triangle, was a scale factor of 1/2 to go from the original to the blue triangle. So 1/2 to get from A prime to A, and 1/2 to get from A to A double prime. So 1/2 times 1/2 is 1/4. So the scale factor to go from A prime to A double prime is 1/4. And if you looked at each of these distances, so 1/4 of 8 is 2. 1/4 of 4 is 1. So this point right here is going to be 2, 1. 1/4 of -4 is -2. I'm sorry, 1/4 of -4 is -1. And 1/4 of -4 is -1. So it's going to get to that point right there. And 1/4 of a +4 is 1. And 1/4 of a -4 is -1. So it's going to get you to that point right there. So using the coordinates and multiplying the coordinates of the A prime triangles by 1/4 takes you to the blue double prime triangle. So they're all related. The green triangle is the dilation of the black triangle. The blue triangle is a dilation of the black triangle. That means the blue triangle is also a dilation of the green triangle, and the green triangle is also a dilation of the blue triangle. Anybody know what that scale factor is? It's going to be the reciprocal of 1/4, or 4. So this is going to be 4 times each of these lengths in the blue triangle. All right, so this is problem number 3. This is problem number 4. The information that you're given in problem number 4 is you have a triangle. ABC is a right triangle, and the measure of angle A is 28 degrees. What are the measures of the other 2 angles? Well, if they're telling you that you're beginning with a right triangle and one of the angles is 28 degrees, that's telling you one of the other 2 angles is 90 degrees. It's a right triangle. So this angle has to be 90 degrees. And so then what I'm going to do is just measure from here out to here 28 degrees. And then the remaining angle is going to add to a total of 180 degrees. Remember that the 3 angles of a right triangle, or actually the 3 angles of any triangle, will line up together along a straight line and form a 180 degree, a straight line of 180 degrees, a 180 degree angle, or a straight angle. It's going to go halfway around a circle, so it will equal 180 degrees. All right, so estimate where 28 degrees is. From here to where in here is going to be 28 degrees. And these are just estimates. It does not have to be exact. It's okay. So this is 45 degrees. This is halfway. So that's 45 degrees, and half of 45 is 22.5. So I'm going to call this a 22.5 degree angle from here to here. Well, 28 degrees is just a little bit more. So I'm just going to estimate it, and I'm just going to call that point right there. That's going to be an angle of 28 degrees to take me out to there. So then what's the rest of this? What does it have to add up to? It has to add to 90 degrees. So this is 90 degrees to go from here to here. So it's another 90 degrees to go from here all the way down to here. So this angle right here, we haven't identified its size yet, but plus 28 degrees, those 2 angles have to add to 90 degrees. So that makes this angle has to be 62 degrees, because 62 plus 28 is equal to 90. And these 90 degrees plus these 90 degrees are the 180 degrees that is the sum of the 3 angles of a triangle. In this case, it's a right angle, 90 degrees, 28 degrees, and 62 degrees. So if you take these 3 angles now and you cut them out, we did this activity before, you cut them out and you reposition them, you can only get one triangle in the end. And that triangle is this triangle right here, 90 degrees, 62 degrees, and 28 degrees. Now you can come up with different looking triangles. They could be reflections, rotations. They could be similar triangles if these lengths are a different length, but they will all be similar triangles. Some of them will be congruent triangles. They will all be, in essence, this same triangle, related to this same triangle. So 90 degrees, 28 degrees, 62 degrees, and this is problem number 4.